Which brings us to our last talk, which is going to be fast in-network GraY failure detection for ISPs. So we're moving from data centers to ISPs, and the talk will be given by Edgar, who is a final year PhD student at ETH Zurich, and his research centers around network programmability and network function offloads, and he will be on the job market soon. So let's give your presentation. Thank you very much.
Right, today I'm going to talk about our work on GraY failure detection for internet service provider networks. Let's start with a simple example. We have these two users trying to access some service in the internet using the same internet service provider network, and suddenly one device here starts to malfunction, affecting the traffic of one user, but not the other. Now the affected user calls the ISP, and a network engineer starts to look into the issue. However, using the techniques they have and the monitoring systems they have, the engineer finds no problem at all. What we just have observed is a permanent packet loss caused by a malfunctioning device affecting only a subset of the traffic, in this case, the lower user. In this presentation and work, we will call such type of failures GraY failures.
Running a little bit late.
To give a bit of background, GraY failures can be caused by many things, but the most common cases are TCAM bit flips and memory corruption, bent fibers and not well-seated line cards, CRC checksum errors, and software bugs and misconfigurations. Now, these errors can affect traffic entries in a different way. For example, it can affect only one single traffic entry, as we saw in the example, one user, and or only traffic for one specific destination, multiple of them, or all of them at the same time. Also, in the way traffic entries can be affected can also affect how packets get dropped a bit differently. All packets could be dropped, making, for example, a black hole of a given entry, or just a few percentages of packets getting dropped. Now, this is not just a toy example. This is happening nowadays in ISP networks. And we conducted a survey on the unknown mailing list, and the vast majority of operators told us that for them, GraY failures are a major issue. 14% of them experience GraY failures every day, 46% every month, and 73% every half a year. And these are only numbers they know because customers have complained to them, since they lack techniques to detect that there is an issue there. Now, I'm going to try to explain why existing monitoring techniques don't work very well. And for that, we need to understand what are the two key things to detect GraY failures. First, we kind of need to collect statistics on all the traffic, because we might be missing like some traffic that is being impacted. And second, we need to do some kind of comparison. This depends on the system doing the detection. Now, current ISP techniques to detect failures fall short at that because they do not collect statistics on all the packets. For example, both active and passive systems, for example, let's say heartbeat protocols, they will only detect a failure if the heartbeat packet gets dropped. In the passive side, we can have, for example, counters in the switch, but those will only detect problems if the counter is measuring the specific thing you want. Now, there has been a lot of work in data center networks in the last years that are actually very, very, very efficient and very, very good at detecting GraY failures. However, they fell short in ISP networks. And I'm going to try to explain you why. We need to first see what is the difference between an ISP network and a data center network. And these are the key differences. First, we have no endpoint control, so we have to discard all end-host-based solutions. And second, we have very high link bandwidth combined with very high link latency between devices. This is like the key difference between data centers. And let me try to show you the problem a bit more graphically. As I said before, such systems need to collect statistics on all the traffic. And to collect these statistics, you need to save some piece of information somehow in the switch. And the amount of information you need to store depends on these three components. First, what is the collection rate, which kind of depends on the packet rate you are receiving packets. Second, what is the amount of information you store per packet? This depends on the system that is doing GraY failure detection. And last, what is the minimum amount of time you need to be storing this information before you can do this kind of comparison? And now, this depends on the link delay, if, for example, two switches are communicating this information, or depends also on the capacity a control plane has, or the speed the control plane can read this information. And here's the key problem. The required memory is way bigger than we have in switches nowadays. With this background, I'm going to introduce you FANCY, our fast-in-network GraY failure detector for ISP networks. And what we did here is that we thought our design such that we can reduce this required memory a lot. And for that, we did two things. First, we reduce a lot the information that the system collects by aggregating the collection of statistics into packet counters per traffic entry. And second, we remove the control plane from the equation by doing both the collection and the comparison in the data plane. FANCY works in between pairs of switches that are directly connected, and it detects failures at the port level. And at a very high level, what it does is that for a given traffic entry that you can decide, it keeps kind of two counters. It counts packets between these two switches during some time. Then it compares these counters. And if there is a mismatching entry here, a mismatching counter, it flags the entry as faulty. Now, this sounds very simple, but it has two main challenges. First, how can we do this packet counting in a synchronized way at very high speeds? And how can we do this process reliably? And second, how can we scale this to many, many traffic entries? We want to be able to monitor all the traffic entries that we have. Let's look at the first issue. In FANCY, in order to achieve the synchronization and reliable counting of packets, we have implemented a protocol in the data plane that uses these state machines, both at the center and the receiver, and it does this for every traffic entry we are trying to count packets for. So the protocol is quite simple. The upstream switch sends a start message to the downstream switch, and upon receiving this message, the downstream switch will clear all the data structures from the previous counting session and will reply with an acknowledgement. Now, the upstream switch will move to counting state and will tag all the packets for this traffic entry such that both ends count this very same packets. Does this process for some time, and it sends a stop packet. The downstream replies with a counter, and the upstream checks if these counters mismatch. If they are different, that indicates that there was some packet drop, and it flags the entry as faulty. Now, this information can be used directly in the data plane. You can use that to react directly in the data plane, or you can report it to a controller if wanted. Now, although this kind of simple counting protocol works very well and it allows you to detect traffic drops for one entry, it does not scale very well. We require for each pair of counters and states machines 160 bits. And let's say we want to track 1 million entries, for example, all the prefixes in the internet. This would require us more than 1 gig of memory, something that is 20 times more than what we have today. So for that, what we did is that we thought, OK, can we have some sort of other type of counter that is more memory efficient? And we realized that GraY failures are kind of sparse. So you can have these million entries, but at the given point of time, you will only have maybe one entry being affected or multiple of them. So what we did here is that instead of mapping one entry to one counter, what we can do instead is we can have an array of counters, W counters, and now to map the packets from one entry to a counter, we use a hash function, and that will indicate in which counter do we have to do to add the packet. Now, as we did before, this process is done between two switches, so the upstream and the downstream, and we will do the same operation. So the downstream will send us the same array of counters, and if there is any traffic entry that has problems, we will have a mismatching counter here. Now, the key here is that we can repeat this process over and over, but in the second counting round, we only count for the traffic entries that in the previous round were hashed in the faulty counter. Now, this allows us that in every zooming step, we will divide the amount of entries we are monitoring by W, and now we can repeat this process for multiple times until we isolate the faulty entry into one counter, which can be identified by the hash path it took from the top to the bottom. Now, although this process, this new type of counter hash-based counter allows us to scale, it has two main drawbacks. First, it increases the detection time, because now it's not just one exchange of counters, but we need to do this multiple times. And two, it decreases accuracy, because we need to detect packet losses for this entry during the multiple zooming stages. Now, so far, I have shown you that we can try to find these kind of failures using two types of counters, the dedicated counters and the hash-based counters. But what we can also do is we can have a hybrid approach, and we can have both types of counting sessions. And then a network operator, given some memory budget, can decide how to allocate the traffic entries. For example, for high-priority traffic entries, can say, hey, I want to use dedicated counters, which are faster and more reliable. And for the rest of the traffic, can use this hash-based approach, which scales, but it's a bit slower and has less accuracy. Now, let me try to show you what is Fancy's accuracy, both in accuracy and speed. And for that, we have software simulations using NS3, we extended NS3, and a hardware implementation. Due to the lack of time, I'm only going to show you two things in this presentation. First, how does Fancy perform depending on the GraY failure and the traffic affected? And second, I'm going to try to show you, can we implement these in today's programmable switches? Now, in the paper, we evaluated many more things, like multiple entry failures, uniform random drops affecting all the entries, and also some evaluations on KIDA traces. But for more information, refer to the paper. I have to say that those results are equivalent, are kind of follow the same pattern than what I'm going to show you now, which is more fundamental. So for this first evaluation, in which we try to see how does Fancy perform for different GraY failures and traffic entry sizes, we use the following methodology. We evaluated both dedicated counters, the first type of counters I showed, and the hash-based array of counters separately, and we only performed single entry failures. However, again, due to lack of time, I'm only going to show you results on the hash-based counters, because dedicated counters will always detect the problem as long as there is a single packet drop. Now, we have set the inter-switch delay to 10 milliseconds, which is kind of an upper bound for ISPs and a worst-case scenario for us. And we run all the experiments during 30 seconds, and if the failure is not detected in 30 seconds, we consider it as not detected. Now, we don't show results, we don't compare with other data center approaches, because they do not operate with this delay of 10 milliseconds. Now, I'm going to show you the results for the hash-based counters, how well do they perform, and for that we use like a 3-layer approach and a 200 millisecond counting session per each zooming. And here I'm going to show you the true positive rate in a sort of heat map, where in the y-axis we have the entry size, bandwidth of the entry size we are trying to detect, and on the x-axis we have the loss rate we apply to that entry. Now here, what you can see is that in all this yellowish area is all the area in which Fancy, the hash-based counter of Fancy, can detect all the failures with 100% TPR for all the experiments. And we can see that if the traffic is more than 1 megabit per second, it can detect those failures for any loss rate. However, as the traffic per entry decreases and the load rate also decreases, we can see that the performance of the hash-based counters start to decrease. And we can even see this area where we have a 0% TPR, but this is more like an artifact of our experiments, because at very low rates and low loss rates, we almost have no packet drops. So I'm going to also show you the detection time of the same experiments, which is the same, similar heat map. So what we can see here is that if we have enough traffic, we detect the failure after 3 zooming intervals, and as the traffic decreases, we start to see detection times that increase. Now, we have implemented Fancy in P4 and made it run into Fino switches, and here I'm going to quickly show you an example. We have these 2 Fino switches directly connected. We send traffic between this link, and we induce a GraY failure for all the traffic. And we evaluated both the dedicated counters and the hash-based counters with counting campaigns of 200 milliseconds, and for the hash-based 3-zooming approach. As you can see here, dedicated counters can detect the failure after 200 milliseconds, and what we do here is that after it's detected, the switch reroutes all the traffic directly in the data plane. And for the hash-based approach, you can see that after 600 milliseconds, the 3 zooming intervals, the failure is detected and rerouted. So with that, I reached the end of my presentation. Today, I presented you Fancy, an in-network fast gray failure detector for ISP networks. And Fancy, what it does these simple counter comparisons. And we showed you that we managed to do it in a reliable and synchronized way in the data plane. We scale those counters by using a hybrid approach, dedicated counters and hash-based counters. And we also showed that it runs in today's hardware. You can find all the code in this GitHub link. We released everything.
What was the biggest challenge that you had to tackle in order to do this?
So yeah, the biggest challenge was to implement this directly in hardware. So the two hardest things were the state machines. Implementing state machines in the data plane it's quite complicated because you can only when you have to you need to save the state in registers, and when you want to do state transition, you need to read the state and know how you will change the state at the very given stage. So that was quite complicated to implement. And then second thing was for the hash-based counters, the zooming part was a bit complicated because we needed so as you were zooming more deep in this data structure, you needed to kind of know what were all in the previous rounds, which were the counters that experienced a problem in the previous round. So you had to save all these in different registers and then read it, and to finish switch. Well, I mean, it was kind of a limitation that we had to do quite a lot of engineering to manage to fit this into the finish switch.
I see.
Hi, Jashi from Alibaba. So one question, since it's a switch failure, how can you trust the switch to detect the gray failure of itself? And then the follow-up question, more philosophical question is, do you believe in-network gray failure detection is sort of free from gray failures?
Right, that's a great question. Well, that's the verifier trying to verify the verifier. Well, yeah. I mean, it's better to have this than nothing, I guess. It's true that our system can also, it can experience problems from memory corruption. So one thing you can try to do here is, I assume you can have you would have to add the control plane and try to involve it into the loop, try to help here as a watchdog. So you could, yeah, I mean, eventually the system, but all detectors, all gray failure detection systems in data plane could have this problem. So yeah, you would need to kind of somehow assist it with the control plane.
Thank you.
Thank you. Last quick question, please.
Okay. So, Kamer Razavi from TU Darmstadt. I saw that the time frame that you are detecting the hash-based issue kind of failures are 10 milliseconds, but in the experiment it's 600 milliseconds, which
No, 10 milliseconds is the inter-switch delay we have between
So what is
switches.
the time period of the hash-based detection failure detection? So because you said that you have an iterative way of detecting the...
So yeah, so for example, if you are zooming 3 times, like we do in these examples, and then we are counting for 200 milliseconds, it's 200 milliseconds 3 times, so 600 milliseconds.
Okay, so what happens for all those packets that are being dropped during that time?
Well, yeah, they are going to be dropped. But I mean, there is nothing, if you don't have such a system, they are going to be dropped for longer because there is nothing that will detect it. So 600 milliseconds is better than having nothing, right?
Okay, so one last small thing.
Yep.
How to reduce the time frame? Do you know? Can you give us some insight about that?
Yeah, I mean, so there are multiple ways. First, you could try to zoom less times, but that increases the probability of collisions that you have in your measurements. So the only way to reduce this time by using the hash-based approach is by reducing the amount of zoomings, but then you require more memory to have the same guarantees. So,
all right, guys. The data, please do it offline. And let's thank our speaker because we have the sponsor session coming up. And we have already taken too much time, and I'm getting flack here. So thank you very much, and great to see you all here at SIGCOMM'.